Hi everyone, this is the science update for Q1 2026. Just a quick note, I am coming down with something, so I'll try and edit out all the sounds of me being sick from this video, but honestly, I probably won't do a very good job of it, so apologies in advance. Right, so like I said, this is the science update for Q1 2026. This will cover the work done by the science team at Open Force Field, largely from January to March this year, although I'll add in some updates from early April as well for ongoing projects. Uh, Here's a quick outline of some of the projects that we have to cover. As you can see, there's actually quite a lot to cover today, so I'll get right into it. First up, a manuscript on the development of AshJC and Sage 2.3 has been accepted for publication, so that's exciting. It probably won't be online yet by the advisory board meeting, but we have been assigned a DOI. I think we've talked a lot about AshJC and Sage 2.3 in the ad board meetings already. There's not much more to add, so just quickly moving on. Next up is the water models co-optimization project. So we've been spending most of Q1 on a roadmap goal of co-optimizing a 3-site water model with Sage that outperforms TIP3P and OPC3. In particular, what we're aiming for here is a co-optimized force field that improves performance on our typical physical property targets of densities and enthalpies of mixing. In particular, some of the outliers that we've identified. Our plan is to start from the TIP3P FB and OPC3 water models as starting points and optimize both the van der Waals and geometry to both pure water and mixture properties. This is part of a wider collaboration between OpenFF, the Schertz Lab, including Barbara, and Li Ping, looking at both 3-site and 4-site water models. As an initial step, Barbara and Chris both looked into whether swapping water models would fix some of the outliers that we see in our water mixture properties. So Barbara benchmarked the performance of Sage 2.3 with a number of different 3-site and 4-site water models, and found that performance improved with Sage 2.3 if we use better ones. So for example, TIP3P FB or OPC3 in place of TIP3P itself. And this is despite the Sage 2.3 parameters being fit to TIP3P. Chris took it a bit further and looked to see if he could improve performance even further by refitting the van der Waals parameters to OPC3 water directly. Surprisingly, in terms of bulk metrics, this actually didn't improve overall compared to just using the existing Sage 2.3 parameters and just swapping in OPC3 as the water model. That being said, we did improve on some of the amine water outliers down here, which is great to see. At this point, we also started stepping back and taking a closer look at some of these outlier points in more detail. And we identified a few further issues. So for example, looking at one cluster of outliers up here, we realized that we had been simulating this lactam form with water, which is not the stable preferred tautomer. Instead, here we should really have been using the lactam form. We eventually had to trace this back to a bug in Evaluator itself, which was inferring tautomeric forms using the INCHI, instead of preferentially or incorporating the use of the IUPAC name, but more on infrastructure updates later. A second consideration was whether we may be ignoring meaningful protonation of amines, which are a group that perform quite poorly with water with Sage. We implemented a new check that searches Kemble or tries to predict pKa's using the pKa learn predictor and excludes amines with pKa's over 11, where we might expect that a reasonably high proportion of the amines are protonated in mixtures with water, and therefore not well represented by the approach that Evaluator takes in estimating the enthalpy of mixing using the same chemical graphs over each component. And lastly, as part of a general survey of thermo-ML, we identified and excluded some outlier measurements. So for example, these points that are more than 10 sigma away from other apparently identical measurements in the thermo-ML database. These actually haven't affected fit so far, but better safe than sorry. So we really did kind of a general re-review of the data available in the public thermo-ML. And we found that the current coverage of core solvents and chemical environments that we're interested in is fairly patchy overall. So this figure is a heat map of the co-occurrence of chemical environments in binary mixtures. And on the top and the right-hand side here, we've labeled not the specific functional groups, but the group that they lie in. So for example, different kinds of ethers, different kinds of alcohols, and so on. And you can see that there's quite a lot of blank space here. The heat map represents the number of data points available for that mixture in a general broad sampled set, and gray represents a lack of coverage. So we're also in talks with NIST to see if we can collaborate on another public release of data to augment our training and fitting data set, and expand our coverage of chemical space to fill in some of these gaps. This is still ongoing, so it's likely that our three-site model will be restricted to public data only, but will be really beneficial to future fits. Also, as part of this effort, the science team has been working with both the infrastructure team and Leaping to get the necessary software stack back in working shape. Primarily, this focused around updates to OpenFF evaluator and force balance, where we needed to get virtual site refitting up and running again in tandem with each other. We've also fixed some other bugs to do with fitting in evaluator as of version 0.5.3, including some issues that touched other projects around OpenFF, such as the lipid force field. We put in a fix for inferring to automatic forms, as mentioned previously, and we're also making evaluator a bit easier to use for the water core optimization project. In force balance, we've also put in a few updates that will hopefully get released shortly. So this includes updates to the virtual site refitting, modernizing to work with the modern OpenFF toolkit, including Nagler charges, as well as some unrelated updates to the GRAMACS and PyMBar interfaces. And lastly, interchange is largely the domain of the infrastructure team, but I thought I would just mention here that we did find and fix a virtual site geometry bug. So if you're using virtual sites with OpenFF, please do use OpenFF interchange version 0.5.1 and above. So we generally at a point where we're about to start with S3 site MVP, where we'll co-optimize parameters to existing public thermo-ML data. As part of this, Michael led a grant for getting us some compute time on the Oak Ridge Frontier cluster. So we're in the process of setting up both FF fitting experiments and refining technical workflows to prepare for a larger grant application down the line. And lastly, this has just started, but Chris is also looking more closely at alcohol and water mixtures. As you can see here, this subset also performs particularly poorly in both densities and enthalpies of mixing. The direction that we're currently investigating is whether rescaling alcohol charges will improve enthalpies of mixing. This is still in progress, so I won't talk too much about it, but you'll probably hear more about it next quarter. On a very related note, we have continued with our roadmap goal of moving away from force balance by constructing a new library for co-optimizing valence and van der Waals parameters with SME and descent. While the cold group have been successfully using SME and descent for optimizing valence parameters, fitting parameters to simulation data such as physical properties requires more management of distributed compute. And we have determined that putting in this new library would be easier to maintain than upgrading the evaluator library. We're also taking this opportunity to add some quality of life improvements and support for anticipated fitting needs. While this currently falls under the umbrella of scientific code, progress here is actually being driven by Matt Thompson from the infrastructure team. In terms of other updates to SME and descent, which currently are also regarded as scientific code, we have put out a new release of SME version 0.17 and are working on updates to descent. SME version 17 or 0.17 corrects a few nasty bugs affecting fits, in particular with periodic systems on CUDA, and also removes the current dependence on amber tools. In descent, we're aiming to add a few features that will also be useful to periodic fits and remove the amber tools dependence as well. This progress is mostly work that is being driven by Joao and Finlay in the collab. This ties in well towards progress on our next major effort, which is refitting a Sage 2.4 force field using SME and descent. So this covers a number of experiments where the overall goal is to work out a good fitting workflow for Sage 2.4. Unlike our force balance workflow, where we fit to optimize geometries and torsion drives, SME and descent currently only support fits to energies and forces of individual snapshots. Therefore, there's still quite a lot of open questions on which data is best used for SME and descent, whether we should use the existing SPICE2 dataset of equilibrium snapshots, or whether we should use our existing dataset corpus of equilibrium data. As shown in Finlay's comparison of per atom force magnitudes, these datasets do differ quite a bit. We ran a few experiments here that I won't go into, but the overall takeaway is that trying to use only our existing dataset of optimized data without off-equilibrium data results in force fields where the bond and angle force constants trend continuously towards zero. This also leads to drift in the equilibrium bond and angle values, And the overall result is much worse performance on benchmarks like relative conformal energies. In parallel, Jennifer Clark has also been experimenting with fits just as SPICE2, in particular investigating whether finer partitioning of chemical space improves performance. Jen has also run a lot of experiments here that I also won't get into this time. They're not quite ready yet to talk about. But the overall pattern, again, is that the force constants here seem to trend towards 0 over the course of the fit. And again, the equilibrium values can drift quite a bit. Our overall hypothesis from these results and from other results that Finlay and Danny have shown is that the optimal training dataset would include a mix of equilibrium and of equilibrium geometries. To test this hypothesis, we want to run an experiment fitting to a dataset combining SPICE and optimized geometry data. So to that end, Jen is applying a library that she developed for the Genentech collaboration for robust chemical perception to the OML25 dataset. We're choosing to use OML25 instead of combining the existing SPICE and GUSI archive datasets to avoid any possible issues that might arise from using different levels of theory. OML25 recomputed a number of existing public datasets, including SPICE, and helpfully, they also took 30% of the geom dataset and geometry optimized this subset, which provides us equilibrium data. It took a non-trivial amount of work for us to convert this data, so Jen is uploading our results to Hugging Face as they complete for public use, and you can find these datasets here at these links. Alrighty, on to the protein force field. To recap the goals outlined for this project, we're aiming for co-optimized parameters for both proteins and small molecules that achieve similar accuracy to existing protein force fields. And we're using amber force fields, most specifically amber 14Sb, as our reference. As a reminder, we are evaluating the performance of each protein force field candidate on several tiers of benchmarks. The first is a rapid evaluation of QM data and small unstructured peptides. The second tier focuses on maintaining protein structure of folder proteins in simulation, as well as maintaining the helicity of a 15-mer. And of note, this tier includes the GB3 protein, as well as hen egg white lysozyme, just because I will be mentioning those later. And the third tier of benchmarks includes a wider variety of protein structures, as well as binding for energy targets. And I won't get into the fourth tier because we're not really there yet. And as a brief recap of the history of the project and where we were at the start of the year, Chapin has done many different experiments fitting Smirnov candidates to various data. Typically, the trend that we've seen with our candidate force fields, which descend from the stage 2.1 small molecule force field, is that they do better than amber on QM, small molecule, and unstructured peptide benchmarks. However, that doesn't translate to good performance on larger folder proteins, and for all fits Chapin tried, where the force field was just trained to small molecule and peptide QM data, we would see secondary structure unfolding with the folded protein benchmarks. The Rosemary Alpha force field released last year extended the small molecule and peptide QM dataset to add in GB3 and the helical 15-mer as training targets, and this did result in good performance on these targets. Across the entire Tier 2 benchmark suite, which includes 4 folded proteins, the Rosemary Alpha performed within range of amber 14Sb on 3 of them. The one exception was for hen egg white lysozyme, where the performance was worse for Rosemary Alpha than for 14Sb. So we also wanted to benchmark on more diverse structures to characterize whether this was indicative of Rosemary Alpha performing poorly, or whether hen egg white lysozyme is just a difficult target to hit. So at the start of Q1, we had just finished running additional Tier 3 folded protein benchmarks, although we had yet to look at the results. And lastly, last year, we also benchmarked the Rosemary Alpha on our standard small molecule benchmarks, and we discovered that it introduced some issues with sulfur and phosphorus parameters. So at the start of Q1 2026, we were also beginning to think about what the release process would look like of taking Rosemary Alpha to a full force field release, and whether we could fix these small molecule issues in a refit without ruining performance on proteins. Okay, on to some of the work that we did in Q1. Firstly, the Tier 3 benchmark results. This is not the complete Tier 3 set, but the results that Chapin looked at seem to indicate that the Rosemary Alpha, in general, has problems with keeping folded proteins stable. Out of the 8 proteins that he looked at, 3 of them deviated more from the NMR model than amber. 4 were similar, and only 1 was better. So that's still a substantial proportion of the dataset where the Rosemary Alpha is not doing well, suggesting that it might be more of a general force field problem. On the right-hand side here is an example of one of the aggregated RMSD plots that Chapin showed for the proteins. So instead of showing a typical time series trace per replicate, this plot combines data from 3 different replicates and plots a cumulative distribution function instead. where a force field having a line more to the left indicates closer agreement to the NMR structure, and more to the right indicates worse agreement. Since we saw such improvement from incorporating GB3 and the helical 15-mer into our fitting targets last time, Chapin then investigated various avenues of adding hen egg white lysozyme data into the training set as well. But neither way that he investigated offer clear directions forward. So some experiments, for example, fitting to NOE distances, resulted in force fields that maintained good performance on GB3 and the helical 15-mer, but using the same iterative approach that worked well for the GB3 NMR fitting, did not correspondingly improve performance on hen egg white lysozyme. Fitting to hen egg white lysozyme PMFs also resulted in force fields with somewhat patchy performance, for example, improving performance on J couplings, but degrading performance for residual dipolar couplings and NOE targets, even for hen egg white lysozyme itself. Chapin also recently took a closer look at PMFs over fine psi for CAP3 Interestingly, this revealed that this amount of force fields consistently have higher energies near the alpha basin than the QM profile. And the amber force fields here in blue and purple reproduce this shape of the profile much better. Chapin tried a couple of things to see if they would shift the PMF, and the profile is improved if he swaps in amber non-bonded parameters. That's the brown line here, although not to the extent of reaching the amber force fields. The other approach was adding CAP3 into the training dataset itself, which resulted in the pink force field, null 3-mer QM. Disturbingly, this didn't seem to shift the profile at all, resulting in questions about how we could improve our fitting workflow. This is going to come up later, and we're still starting investigations, so I won't get into that much here, but here is the state of things at the end of Q1. On a similar topic, though, we have been exploring the general question of QM fits with rosemary. With our small molecule benchmarks, we noticed that the rosemary alpha has some problems with sulfur and phosphorus parameters, resulting in geometry optimizations with very odd angles. The main question we want to answer is if we can refit rosemary alpha to QM data to fix this behavior without degrading protein benchmarks. So Chapin ran a couple of experiments where he refit the rosemary alpha to QM data in two ways, one where the torsions were all free to move, and one where the protein-specific torsions were frozen. Both fits unfortunately resulted in worse performance on tier 2 benchmarks and will probably require another round of NMR fitting to get back to rosemary alpha level performance. So you can see these two fits in olive green and red here, and you can see that the chi-squared value is much higher than the rosemary alpha value in orange. The next experiment we're planning to try next quarter is to refit with type price across all torsions, not just the protein-specific ones, since some of the general torsion parameters in the rosemary force field are also involved in secondary structure. Last but not least, I just wanted to introduce another effort that has started up in collaboration with the infrastructure team with Ashley, which is starting peptide benchmarks with Smirnoff candidates. One of the big advantages that rosemary will bring is being easily applicable to non-standard peptides, including cyclic peptides. So Ashley is starting to set up a small benchmark set of peptides to compare performance with other peptide and protein force fields on these targets. Alrighty, on to another ongoing project in the consortium, which is improving lipid parameters with the goal of reproducing membrane properties in simulation. This is being led by Julianne in the Schurz lab, and she's starting off with phospholipids, which have several key parts: the head group with a phosphate group, a glycerol linker, and hydrocarbon tails. So as a sub-goal, this project aims to improve alkane, alkene, and phosphate parameters. A targeted approach has worked well for alkane and alkene parameters. Julianne was able to optimize the force field starting from stage 2.2.1 to alkane density and enthalpy of vaporization data, which substantially improved performance in those areas, and porting those van der Waals parameters to stage 2.3 retained performance. One interesting outcome from this experiment was that the force field that performs best on alkane torsion profiles relative to QM overestimates the trans-Gauss ratio in simulation more so than a force field that slightly underestimates the relative minima, underscoring the need for fitting and benchmarking on condensed phase data. However, she ran into difficulties extending this approach to phosphates. Even an optimization and benchmarking on a single phosphate torsion drive became complicated, as the constrained optimization that's used in torsion drives often results in a phosphate geometry that was quite different from the QM structure. We're still experimenting with alternate approaches, such as converting the constrained optimization to one that uses restraints instead. So we'll have updates on this in the next quarter. Okay, so a quick update on QM datasets run by Aditya Jennifer Clark. The Sage 2.3 optimization and torsion drive fitting and benchmarking datasets are now available on QC Archive and Zenodo for easy download. We've also added a few new datasets, an additional torsion drive dataset for lipids, multiple datasets expanding the chemical diversity of sulfur, nitrogen, and phosphorus groups, and a dataset re-optimizing torsion net 500 at the OpenFF level of theory. The first two are largely for improving phosphate fits, and the last is for use as a benchmark set. For the in progress section, we're really excited that the architecture dataset for diverse organometallic ligand complex structures is finally up and running. This was the result of a huge amount of work from Jen and will really expand coverage for the Genentech collaboration. She has also recently filtered a subset of problematic geometries from SPICE, which are largely rare chemistries that Sage doesn't perform well on, and is running geometry optimizations on these as additional fitting data. While we're on the topic of collaborations, Jen has also been working closely with OpenFE to collaborate on building out a more standardized benchmarks repo. This includes support for both protein ligand binding free energies and absolute salvation free energies. Includes both a set of standardized systems as well as code for discovering these, stores a standardized set of partial charges in the repo, and contains examples of building or using previously generated networks. We're really excited that this is nearing completion, as this repo and this project and collaboration will make it much easier for OpenFF to run our own benchmarks for future fossil fuel candidates. And lastly, onto a few odds and ends. One item that Jen uncovered during her collaboration with the OpenFE benchmarks repo is that our current scripts actually interpret the molecules from the Minnesota salvation set incorrectly, in particular during the conversion step where we infer the chemical structure from the molecule name. Some of this is because the molecule name itself is underspecified. It doesn't specify which isomer to use, and we wind up using a different one than is in the paper. In other cases, though, it's likely due to an underlying issue with how we're parsing IUPAC names. It turns out this is very sensitive to any modifications to the input. So for example, adding a space to phenylformate results in a different structure and actually the correct structure here. We did a preliminary check, and none of the incorrectly parsed molecules were present in our Sage benchmark sets, and we have now identified and removed them for future benchmarks. While we're on the topic of bugs, a somewhat thornier bug is one that we've recently discovered impacting our calculation of AIM-1 charges. And this is specifically using OpenEye software. This bug affects atom types that should get assigned atom type 23, which is a highly delocalized lone pair nitrogen. And the canonical example given is the nitrogen in indole. With this bug, however, this type actually gets assigned type 21 instead. This error can result in very different charges on the nitrogen, such as a 0.4 elementary charge difference. And we notified OpenEye about this last year. Since then, they've gone back to us, and there should be a fix coming in the next release of the software. But this bug has now been present in OpenEye charge assignment for multiple force field fits over a number of years. We wanted to look at whether Sage had been negatively impacted by this bug and whether users should upgrade their OpenEye versions when the fix came out. So we did a quick analysis of the Sage 2.2.1 benchmarks, and we broke down molecules by their BCC differences by OpenEye and AmberTools. And we did this because AmberTools doesn't assign the indole nitrogen incorrectly, which is actually how we discovered the issue in the first place. We were looking into a systematic discrepancy between the two toolkits. We found that the ring nitrogen differences typically fell into the bin between 0.4 and 0.6 of an elementary charge difference, which is this purple line here on this plot comparing relative conformal energies. You can see that this purple line actually arguably performs better across DDEs. It has lower differences in relative conformal energy than the bins with lower charge differences in blue and red. So our main takeaway here is that Sage was not negatively impacted by the bug, and it's likely that the parameters had been fit to compensate for it. So when the next release of OpenEye is out, we actually recommend not updating to maintain consistent charge behavior with Sage. Okay, thanks for holding with me to the end here. Our major focuses of the second quarter will be continuing on with the projects that I've gone over throughout, as well as some that I haven't gone into, like the next generation Espaluma work. We will, of course, have the annual workshop in May, some other conferences, and I'll also be offline for a while. So in general, we're anticipating that Q2 will be a bit slower pace than Q1. But as always, we'll aim for concrete progress on roadmap items such as refitting a water model, working towards a protein and lipid force field, continuing collaborations around OpenFF and OMSF, and core projects such as constructing the DimSim package and progressing towards stage 2.4. So you can hear all about this next time. Thanks for listening.